Hello all, welcome to my course on methods of adhesion measurement theory and practice. Today we are on lecture 17. In the last lecture we talked about Hertz contact mechanics, and today I will briefly recapitulate what spoke to yesterday in the last class, and then we will discuss about some ideas about surface energy and adhesion and surface interfacial energy. So, in a sense, in the last class we talk about contact of two surfaces which are two solids, non-conforming solids, which at zero load contacts at a single point or a line, and then as we apply the load the contact area increases, and either it is a circle or let us say it is an ellipse or a rectangular like that. So, at zero load let us say talk about this particular point A. So, the gap between these two surfaces at the point A x y is z 1 plus z 2 here, and so therefore, it is h x y. So, if you are discussing in the x y coordinate, and if we have in the r theta coordinate, theta symmetric r z coordinate let us say, so then it will be h as a function of r. So, now when we apply the load as it is done here, the contact load, total load is P, and depending on the modulus or the deformability of these two bodies, the gap decreases to a different extent. Let us say the point of application of the load here for the solid, this decreases by delta 1 here, and for solid 2 it decreases by the point moves by point of application of load moves by distance delta 2 here. So, the point of applications of these two bodies come closer by a gap by a distance delta 1 plus delta 2, and then I discussed in detail that the gap at the point let us say A comes out to be decreases to from h x y, h as a function of x y to h x y minus delta, that is delta 1 plus delta 1 plus delta 2 is equal to delta here plus this nu 1 z at z is equal to 0 and nu 2 at z is equal to 0. So, these quantities are the vertical displacements at this particular point x y and like that. So, this is what we had discussed, and we said that if this quantity, the whole quantity is equal to 0, then this particular point lies at the contact area, and if it is greater than 0, then it is lies outside the contact area. So, we talked about that, and so therefore, we talked about this solid of revolution. So, in a sense this is a solid of revolution means a surface which is revolved about an axis, and so then you form a 3-dimensional object. So, here for example, this is a sphere, there are two spheres of two different radius of curvature let us say r 1 and r 2, and so the gap initially here is h r is equal to r square by 2 r capital R, and here this gap decreases to this particular quantity. So, it is in at the contact. So, therefore, the total displacement over here vertical displacement, vertical deformation is given as the total deformation of these two spheres will be given as v 1 z at z is equal to 0 and v 2 z is equal to 0, and that is equal to delta minus r square by 2 r. And if you see from the top, the contact area will look like this circle. So, what we are interested in finding out is that under this load what is the kind of pressure distribution that happens within this contact area of loading, because if we can know what is that kind of distribution that happens, then we can find out that how much load has to be applied if we want to separate it, or let us say we can do other calculations. Now, at this point the how exactly it was found out, or like by thinking by making some very important assumptions. So, one was that this particular contact is frictionless. So, that is when you apply the load, it is only the normal stress that acts at the contact area, but no friction. And second thing is that this r, that is the contact area, let us say this distance is let us say r here, or let us say this is a here. So, that distance is much smaller, is with respect to the r 1 and r 2, and this is also r the relative radius of curvature. So, here by making this assumption, okay, what it has been done is that what we have thought about is that this contact area that is actually much smaller with respect to the dimension of these two spheres, and as a result this situation is very similar to the elastic half space that we have talked about earlier. So, the elastic half, so the results that we have derived for elastic half space, that becomes applicable, okay, for this case. So, remember that this equation that we have derived is from geometry, this is not from any physics, any physical insight. But when we make this assumption that it is an elastic half space and there is no friction at the contact area, then we can apply the relations or the theory that we have developed for the elastic half space, and that is exactly what was done. So, for example, in an elastic half space, when you apply the pressure of this particular distribution P 0 into 1 minus r square by a square square root, okay, when you make this particular distribution and the total P is capital P is the total load that can be given by this and this obtained by integration, okay, so that this V looks this, the vertical deformation of this vertical deformation at any location r, okay, of this contact area that is given by this equation, and so this equation matches very well with this equation here, that V V at z is equal to 0 is equal to delta minus r square by capital 2 r. And since this there is correspondence between those two relations, and so therefore, we can write delta as equal to 1 minus sigma square by E into, here it is 3 p by 8 a cube into 2 a square, like that, and 1 by 2 r is equal to 1 minus sigma square by E and 3 p by 8 a cube into, yeah, like that. So, now if you remember this 1 minus sigma square by E, so that in our case will be 1 minus sigma square by E. So, that will be given as 1 minus sigma 1 square by E 1 plus 1 minus sigma square by E 2 here, sigma 2 square by E 2 here, because there are two different solids having elastic modulus E 1 and E 2 and this Poisson ratio sigma 1 sigma 2 respectively, like that, and 1 by r, okay, that is will be reduced relative radius 1 by r 1 plus 1 by r 1 plus 1 by r 2, it will be given by like. So, we have derived these expressions over here over in the last lecture. So, here it is like that. So, this is what we had now having this. So, once we know that this is the pressure distribution at this surface, then we can actually do many more interesting things when you consider there is adhesion between these two surfaces. So, so far I have not talked about adhesion, we have only talked about the contact mechanics. So, we will like to talk about adhesion now, and so in the today's lecture therefore, I am going to talk about surface and interfacial energy. So, we will give some idea of surface and interfacial energy, we will show in the next few lectures that how to measure the interfacial energy, how to estimate the interfacial energy, how to measure the surface energy and so on. And then we will once again come back to contact mechanics, and at that time we will discuss the contact mechanics with adhesion. So, how the idea of this surface energy interfacial energy came? So, here for example, Van der Waals in 1873 first proposed the concept of general attraction, okay, or attractive interaction between neutral atoms to account for certain properties of non-ideal gases and liquids. So, it was so three different phenomena were thought to be contributing to these Van der Waals interactions. So, these are these three listed here. So, described one described by Keesham, another described by Debye, another is by London. It all involves some dipole-dipole interaction. So, in one case this is a permanent dipole interaction, another case it is a permanent dipole, but induced dipole interactions. In the third case it is fluctuating dipole induced dipole interaction. So, I will describe in brief that what are these three ways of describing this van der Waals interactions, and so in essentially it is something like this. So there are molecules which have got this electron cloud, and because of asymmetry in the electron cloud, there are the electron cloud is not uniformly distributed around the nucleus, or so as a result there are actually polarity. So for example, this H2O molecule, this hydrogen, this oxygen has got is more electronegative with respect to hydrogen. So therefore the oxygen draws the electron towards itself. So as a result, here this particular molecule in one end there are more electrons. So it becomes negatively oriented, negatively charged in this end. In the other end it has got more positive charge. So therefore because of this difference in the negative and positive charge, there is it is called a polar molecule, there is a permanent dipole moment that exists. So for an isolated water molecule, this dipole moment has been estimated, and this is estimated to be 1.855 dBi unit. So 1 dBi unit is given something like this. So now this value, now when the molecule H2O is present in bulk, so it is under interaction with many other molecules, so it becomes further polarized, and as a result its dipole moment actually further increases. So it increases to 2.4 to 2.6 dBi unit. So it is like that. So this is what happens for a polar molecule. Now it is also happens that it is not all case the polarity dipole moment will be some finite value. For example, this CO carbon dioxide molecule, which is kind of linear. So it has got 2 bonds in both sides, CO and CO, and there are dipole moment for each of these bonds. So this bond and this bond, each bond. So these bonds polarities are different. So as a result, there are because of the symmetric arrangement, the polarity that cancels each other. So as a result, the net polarity of this molecule turns out to be 0. So it is not essential that for all cases, all even if the atom is electronegative, the molecule will have finite dipole moment. So for example, CO2 does not have any dipole moment. On the other hand, H2O does have. So the asymmetry of the geometry, that is important. So so what happens is that, let us say there are permanent dipole, like the one H2O that I said, and then there is another permanent dipole. So when there are 2 dipole molecule like that, then there are dipole-dipole interactions. So these are actually permanent dipole with another permanent dipole attractions and then interaction, and when this positive charge that interacts with negative charge, there is attraction, and when the negative and negative comes together, closer than repulsion. So both attraction and repulsion can happen depending on how the molecules are able to see the dipole, the positive charge or negative charge of one molecule sees the charges in the other molecule. So this particular interaction was proposed by or described by Kissam. So it is called Kissam's interaction. Now here, for example, like there are these dipoles, and there is attraction over here, there is attraction over here, attraction, but then it can be repulsion over here because negative comes together. And then in the condensed phase there are dipoles in all orientations. So there are both attractions and repulsions, and you will have some net value or something like. Then there are actually interactions in which there is one permanent dipole molecule. So this is a polar molecule. So this molecule is in contact with another molecule which does not have any dipole moment. This is a non-polar molecule. So but then this dipole can induce polarity in the other molecule, means like it can deform or it can reorganize the electron cloud around its nucleus. So as a result, there will be like this positive charge over here can induce negative charge in one side, and so therefore there will be attraction between them. So this particular interaction called permanent dipole induced dipole in interaction. So in a sense, this is a polar molecule, this is a non-polar molecule, and the polar molecule can induce some polarity in the non-polar molecule, and then there is interaction. So this particular interaction is described by dBi. So there is some amount of force there that happens because of this interaction. For example, that oxygen has no net dipole moment, but there is H2 here, let us say. Okay. So, the H2 has dipole permanent dipole, it is dipole moment, and then H2 can induce in oxygen the dipole, the polarity, and as a result there will be the electron cloud that gets deformed, and there is attraction between them now. So, this particular effect, okay, is happens. So, dipole of water induces dipole in oxygen via distortion of electron cloud in the oxygen atom molecule. It is like that. So, this is kind of one kind of interaction, second kind of interaction. Third kind of interaction is that we have got a molecule, okay, which has got fluctuating dipole moment, in the sense that the molecule does not have permanent dipole in one particular manner, but it can have dipole moment, and but it is fluctuating. That means for a very small fraction of a very small time it can attain polarity, and when it attains polarity, that is called instant dipole moment, and that can happen because of various factors. Asymmetry can be one, there is always some amount of asymmetry in the molecule. So, now this instantaneous dipole that can induce dipole moment in another molecule, okay, in a molecular atom, the second molecular atom. So, then when that happens, this is called induced dipole, fluctuating dipole, induced dipole interaction, and this was described by London. So, as you notice that the two interactions, for example, here one proposed by Kissam, in another proposed by Debye, in both cases we need a permanent dipole, okay, permanent dipole for this interaction to happen. However, for this case London, this particular case, we do not need a permanent dipole, there are fluctuating dipoles, and that fluctuating dipole okay, it gets this instantaneous dipole moment because of asymmetry, and that induces dipole moment in a second atom. So, that is called the this is described by London. So, this is called the dispersion interaction, and for example, here there is a helium atom, instantaneous uneven distribution of electrons, okay, and this is a nonpolar helium atom. So, this helium atom, so one of the helium atoms, let us say, it generates some dipole moment, and now it induces dipole polarity in a second atom, and that way now the interaction that happens. So, this is described by London, and in this case we do not need a permanent dipole, it is a fluctuating dipole that induces this interaction. So, now in all these cases, all these three interactions, the energy between atoms or the small molecules decay very steeply with distance. So, that means they are essentially very short range interaction. So, it is so it is given by like this, let me just draw it. So, let us say this is the interaction energy represented by so van der Waals interaction energy, that is represented by d here, let us say, and this is d here. So, now this interaction energy is attractive, so it is decreases like that. Now, this is let us say goes as 1 upon d to the power 6. So, what it means is that as gap decreases, this factor, this 1 upon this increases, it becomes more and more negative, there is a negative sign there. So, that is why it is attractive. Now, what happens is that when these molecules or atoms come very close, okay, they cannot come closer than a certain distance, because then there is a repulsion comes into picture. The repulsion is not talked about the van der Waals interaction, it is only the attraction part only van der Waals interaction that describes, but there is also a repulsion. Okay. So, we will not much worry about the repulsion fact in our course anyway, but then you know that there is a repulsion, and because of that, okay, the repulsion works something like this. So, the total force comes out to be something like this. So, there is an equilibrium distance beyond which the molecules or atoms normally do not go closer. Okay. So, it looks something like this. So, in this portion there is attraction, and then when it comes very close, two molecules come very close to each other, okay, then there is a repulsion between them, and that is called bond repulsion, and because of that, that is also very short range. So, in fact, that goes as 1 by d to the power 12. Okay. So, van der Waals interaction goes as 1 by d to the power 6, and the bond repulsion goes as 1 by d to the power 12, right, it is like that. So, it becomes effective at when the d becomes very small, that means. So, now only van der Waals interaction is considered mainly important between macroscopic bodies in condensed systems, because that is present in all kinds of bodies. It does not necessarily have to be a polar, it is even non-polar, not having permanent dipole moment molecules will also show this van der Waals London van der Waals interaction, which is also called the dispersion interaction. So, it is 1 by d to the power 6. So, let us a small example here. So, two non-polar molecules okay, are separated by distance, let us say 50 angstrom, that means 5 nanometer. The van der Waals constant for the interaction is C6 that is given. So, C6 that is 6 into 10 to the power minus 77 joule meters to the power 6. Calculate the van der Waals force. So, remember, so that is the van der Waals interaction energy. So, the force will be van der Waals force VdW, that will be equal to minus of del V VdW by del D, okay, like this. And so, that is the force. So, is minus plus here. So, it will be d to the power minus 6 here, and this is C6 and d to the power 7 like this. So, the calculate the van der Waals force will be like that. What happens to the force if the separation is half? So, now we have to calculate this, and we can calculate by putting the numbers. Let us say it is 6 into this is 6 into 10 to the power minus 77 here, and this is d is 50 angstrom, this is 50 into 10 to the power minus 10 meter to the power 7 here, okay. And so, now we have to see in the calculator what exactly this value will be. So, this value will come out to be about here like this. So, 4.61 into 10 to the power minus 18 Newton, right, like that. Now, if the separation is halved, so that means d is now halved. So, here it is d to the power 7. So, know that the force now increases by more than 100 times, okay. So, it has to be multiplied by 2 to the power 7. So, the force will decrease, force will increase by that much. So, like that. So, this is basically the magnitude of the force, 5.9 10 to the power minus 16 Newton. So, the three interactions of intermolecular, these are short range. Now, to obtain the interaction between macroscopic bodies, these forces were to be added over surface and volume. So, remember that this force defines the interaction between two molecules, okay. Although we are concerned with macroscopic bodies. In the case of macroscopic bodies, we will supposed to have one body and then there is a molecule, let us say. So, what is normally done is that you find out the interaction of this molecule with all the molecules present in this macroscopic body. So, let us say this is a plate, okay, and then when you do that, okay, this d to the power 6 dependence, the van der Waals interaction, that energy, that V goes as VdW, that is goes as 1 upon d to the power 6, that decreases, okay, that is number 6 decreases. So, it becomes somewhat long range, but now when you further integrate it between, let us say this, instead of having a point molecule, let us say it is a sphere, or let us say it is a another macroscopic body. So, when you do that, so you need to do further integration. So, this dependence further the exponent, okay, on d further decreases. So, that way this force then becomes over a longer range, okay. So, Hamaker developed this theory in 1937 and showed that between macroscopic bodies the force turns long range. So, he essentially integrated this force over all the different molecules. So, for example, if the dispersion energy between two semi-infinite parallel flat slab it decreases. No? So, now the interaction becomes d to the power 2 1 by d square, for example. So, this A is called the Hamaker constant. So, Hamaker constant I will just talk about how exactly look like, but there is a constant called Hamaker constant. So, now that is the way it comes. So, now this dependence of course varies differently. So, little bit about the Hamaker constant. So, remember that I am not describing in very detail about these interactions, I am just giving you some idea overview of how this interaction works and like that. So, now when these two semi-infinite slabs are placed at a distance d apart, the interaction energy decreases, goes like this. So, here it goes as 1 upon d square. So, that means that is the way the interaction energy depends on the distance between them, and this particular constant A12, because there are two solids 1 and 2. So, this A12 Hamakar constant, that is related by this equation. Now, this Hamakar constant is essentially determined, okay, from electrodynamics and all kinds of quantum mechanics, all those ideas, right, and their fluctuations and oscillators. So, all those concepts are there. So, therefore, like I will not go into detail there. So, this N1 and N2 are the number density of oscillators in body and body 2. K is a Boltzmann's constant, capital T is the temperature in degree Kelvin, and this alpha 1 and alpha 2, these are called polarizabilities. So, the molecule is more polarizable, means its Hamakar constant will be higher, it is like that, and this polarizability depends upon this complex frequency, okay. Omega n is the frequency of oscillation of let us say nth mode, and so I omega n, so that is the nth mode, and so the polarizability expressed along the complex frequency axis, that is the way it comes out. So, basically these relations, how alpha 1 depends upon I omega n, alpha 2 I omega, so those relations are there, okay. So, those relations are there, and those relations can be obtained also from the relations are there in terms of the velocity of light, then the refractive index of the light in this material and all that. So, those theories are there, okay. So, that can be applied, and so you will see that this A12 therefore, okay, depends upon absolute temperature, velocity of light in vacuum, permittivity, quantum number of oscillations, frequency of relevant oscillation, so all this dielectric susceptibility and like that. So, that is the way these relations are set, and one can actually estimate it. For our examples, we will get the A12 Hamakar constant if we need it from literature. So, that is not a problem. So, I will stop today after solving this particular problem. So, problem 2, a spherical nanoparticle of radius r 20 nanometer is interacting with a flat surface from which it is separated by distance 20 angstrom. Consider the Hamakar constant as this, which is the order of Hamakar constant. So, you can ask me what is the magnitude of Hamakar constant, it will be of 10 to the minus 20 joule for most cases, it will be 2, 5, 3 like that. Obtain the interaction energy between the particle and the surface. So, as I was telling you that the interaction energy, okay, that the exponent on this separation that decreases now. So, now it is given by this. So, this is the way it can be, so it can be derived, and people have derived that. U is equal to minus A is the Hamakar constant into r by 6d, r is the radius of the particle here, and it is in interacting with a flat surface, remember that. So, what is the interaction energy? So, it is minus A and something. So, there is an attractive interaction, and so it is decreases, and here they put the values of d here and the value of r here. So, r is 20 nanometers, 10 to minus 9 meter, and it is at a distance 20 angstrom, so 10 to minus 20 here, and like that. So, it comes out to be this many joule. So, that is the way this kind of problems can be assessed, and we will see that how we get the idea of surface energies or interactions in the next lecture on this topic. So, interaction energy between two spheres, the radii of which a distance between d much smaller than r1 and r2 can also be derived, people have derived this also. So, here this A minus A by 6d remains here, and r1 r2 by r1 plus r2, this is an effective radius of the geometry. I will stop here today, and I will take up this surface energy aspect once again in the next lecture. Thank you for your kind attention.